Now the division subtraction law for logarithms is pretty much the same as the multiplication and addition one, except it's of course using the other law. The index law that we know is that when we are dividing index expressions, and whether it's written this way or as a fraction, we know that what we need to do is keep the base the same and subtract the indices. So that's what's happening here. We're subtracting indices because each of these are indices, and we do this when we are actually dividing the numbers. Now the first proof I have here is really similar to the one that we looked at a moment ago. We have a to the power of everything on this side of the equation. Okay, now we know that if we are subtracting powers, we must be doing this. So we can always break it up and make it look like that. And that's exactly what I've done here. From there we can say, well, we know the law that says you can rewrite any number as a power of something, as long as it's something to the power of a log, where the base of the index number and the base of the log are the same. So we can rewrite something like that. We know this rule. So I've basically taken this and said, hey, that's just x and that's just y, so we'll rewrite it more simply. We could also then use this same law again and say if it works for x, it'll work for x over y, and I'll have x over y up there, which is what I have. So we've got a to the power of this equals a to the power of that. So all of this equals all of that. That's the way the proof works. Now we can also do it another way, similar to how we did it with the multiplication and addition law. So we can actually just break it down and say, let's let that first expression there equal, say, m. And let's let that second one there equal n. Now we can rewrite both of those and say a to the power of n equals x. And over here, a to the power of n equals y. Okay, how does that help? Well, up here on the left-hand side of the equation, we have the log base a of x minus the log base a of y. And that's equal to, well, we've just defined that as m, and we've just defined this one as n. Okay, but meanwhile, on the right-hand side, we have the log base a of x over y. Now, we've just made an expression for x. We've said that x is all of this, and y is all of that. So we can say that we can replace x with a to the power of m, and replace y with a to the power of n. Okay, now we know from our experience with the index laws already that when we have that situation, to solve it, we need to just put a to the power of m minus n. So that's our next step, a to the power of m minus n. And we already know from this other rule that whatever we have down here and up here are equal to each other if we can get rid of these two operations, the exponential and the log, which cancel each other out. So this whole expression here is just m minus n. So the left-hand side is m minus n and the right-hand side is m minus n. So clearly they equal each other. Now how do we use this law? Well, we use it to simplify logs. We're either using it to take two logs that have been subtracted and realise that we can bring them together, but we also use them to take logs and actually tease them apart, because sometimes when we do that we can make a bunch of different expressions that just show another disguise for the same number. And sometimes by making like terms you can then rearrange them in ways that are useful. So one like this, we know that we have to keep our log with the same base, and it's really just a matter of doing 2 divided by 3. And we're done. For one like this, we're just breaking it up the other way. So we can take log of base 10, 1, and subtract log of base 10, 4. Now once you do that, you might notice some things. For example, this part, 10 to the power of something is 1. Well, anything to the power of 0 is 1. So this whole section here is really just 0. So this whole thing really just equals this part here, which is minus this, like that. Okay, so we've rearranged it to look different and it's come up looking a lot simpler. Now, this next one's interesting. It's a decimal, not a fraction. When you have a fraction, it's very easy to see how you can break it up directly. With a decimal, you've got some choices. This is 4/10, but from year 7 to 10, you've probably learnt to do this in your head and say 4/10 is not as good as 2/5. Well, let's have a look at 2 ways that we can do this. If we break it up and say it's 4/10, then we would have this. Okay, now this section here, 10 to the power of something is 10. This whole section here is just 1, isn't it? And this section here, we can actually break up with the multiplication law because it's a 4 and we can say it's 2 times 2. So if we do that, we've got log base 10 of 2 plus log base 10 of 2 minus 1, this whole section here. Now, these are like terms, so if I have 2 of them, I can combine them together and say I've got 2 lots of those. I've got 2 of these log base 10 of 2's minus 1. Now, if I'd chosen the other way to go and said, no, this is 2/5, I would have an answer that looked quite different. Now, how do you know which way to go? Well, sometimes it's a matter of just trying something and seeing what happens. If I have it looking like this, I can't really go any further because these are both prime numbers, so I can't split them up any differently, and neither of them give me an answer that's sort of easy to come by. So it turns out that this whole expression here must be equal to this one. Now, which one's better? Well, both of them could be handy for doing different things with. So you need to understand that logs, you should be able to play with them a variety of ways, get a bunch of different expressions that are all equal to each other so that you can use them as required.